the transformer models so far are quite bad in using very long sequences of data, in this case text, as input. If we try to identify individual problems for this, it mainly comes down to the following three. There are a few more, but these are the three major ones. First, transformers are known to extrapolate very poorly to context window sizes that go beyond the context window that was used for training. For example, most open source models today, like in the visualization I have here, have been trained using data in the scale of few thousands of tokens, which correspond to a few pages of text. So anything beyond this length seems unknown to them, and they don't know how to handle it. A second, even more fundamental problem is that in the way that softmax attention is structured in plain transformers, past information starts to lose its meaning, because we basically apply a weighted average over a lot of vectors representing all previous tokens together. So after a while, it simply becomes too noisy. And to give you some intuition for this, this is a weighted sum, for example, that softmax attention calculates. So imagine that you give it to an LLM a sentence with the final word being mouse. And the only thing that it has seen so far is only a few other words that contain meanings that can be somehow associated with this word. In this case, it's very likely that these words will be largely consistent with a single meaning of the word mouse. In this case, a computer mouse. So the transformer will shift the embedding of the general word mouse to represent this. However, now think of the case that your context is way longer. Let's say, for example, a whole book. Quite likely containing conflicting information about the same word, right? Then you can imagine how by just averaging this information together, it is very easy for the model to be confused and create a mixed embedding of that word and represent something mixed that is not really corresponding to something meaningful with an effect that will propagate to other layers of the transformer with catastrophic consequences. Finally, a third...
Sorry to interrupt. So what you're saying from this slide, if I understood you correctly, is that the longer the context becomes, we will have multiple meanings of the same word that can get, or multiple directions towards the same word that will make the transformer confused?
Yeah. Basically, the way that this weighted softmax works, it becomes more and more likely that the transformer will be confused using embeddings from different things that are not supposed to be used together, and start representing something that has mixed meanings.
Okay.
This is what I meant. And finally, there's a third problem, which is the huge computational and memory cost that comes with inference for long context in LLMs. Because again, we need to calculate a weighted sum across all previous seen tokens and across all layers and attention heads every time we calculate we infer a new query, a new token. Just to store all this becomes prohibitively expensive, even for very small models, like 7 billion models like Llama or Mistral. So you can imagine when we're talking about bigger models, that's impossible to store in devices today. So all those are well-known problems, and there's a lot of work trying to solve those. However, I'd say that most work so far has been around the first problem of extrapolation, with very promising results, but still not tackling the other two. The other two have received much less attention in the context of long context LLMs. So they are exactly the ones that we are aiming to tackle with our work here. For both those problems, a very promising direction to take is to somehow find areas of tokens that the tokens have seen before that can be considered relevant to the current task. As in, find the time that you learned the necessary information and then try to use it and retrieve these tokens exactly, instead of using all the context window that you have. This can be easily shown to be equivalent to having the whole context in a transformer, with the rest of the noisy areas suppressed to zero. For example, the areas in my initial mouse example that indicate an animal mouse, right? So that, in theory, would become much easier for the transformer to understand what you're talking about. And then you can apply a softmax only to these important tokens. So if you think about that, that's like a type of hierarchical attention, right? Although the literature doesn't sort of like define it like that, it is like a type of hierarchical attention. Also, since you process only very few tokens in this particular type of softmax, it's massively less expensive computationally compared to processing all the groups of tokens, given that you have a way to recall specific areas of the tokens. But how can we identify which areas of the context we need to recall, as in which groups of tokens to recall? Looking at the literature, the only solution that we are aware of is this very recent model called InfLLM that segments the context window of the LLM into a number of groups that all have the same fixed size, importantly. And instead of recalling individual tokens, recalls whole groups with the highest similarity using k-nearest neighbors. This model has already shown some signs of improved performance to any other solution with for long context. So we can consider it state of the art, and we used it as our baseline in this work here. But there is still a lot of room for improvement and new approaches that's coming out every day, because yeah, the problem of long context is far from being solved. So here is where we come. To solve this huge problem in LLMs, we decided to take inspiration from the human brain, and this is for numerous reasons. The brain, first of all, is the only intelligent device we know so far that is able to organize and retrieve episodic experiences across vast temporal scales, spanning a whole lifetime, actually. And it's particularly impressive that we always tend to remember automatically the most important information while ignoring everything else, right? So we do basically follow this hierarchical form of attention I mentioned before. And this is despite the fact that we are receiving so vast amounts of information every day. For example, imagine that only our eyes receive about 12 gigabytes of data every single day that we are awake. So somehow we manage to get rid of all this noise and only recall and store the meaningful information for every task. And in fact, the basic principles that cognitive neuroscientists today think that allow the brain to be so efficient are not very different from how LLMs work today, transformers in general. For example, like in LLMs, the most widely accepted hypothesis is that the brain acts exactly like what we call in machine learning a generative model. We keep predicting what we're going to sense or think or even do next. And this extremely simplifies the brain's job, because we only need to pay attention to the experiences that are not predicted well from this generative model of ours, as in the experiences that are surprising. We use the word surprise and prediction error here a little bit interchangeably. So this surprise is mainly when we think that the brain actively cares about processing the information it receives. And if you somehow measure it, you see that the brain activity is high in instances with high surprise. And to give you an example, and again, an intuition on this, of high surprise measured over time, imagine the reaction of your brain if one summer day you wake up and suddenly you see snow. Obviously, the brain's generative model, considering the context of being summer and that previous days were sunny, would predict that this morning will also be sunny as well. I'm trying not to make a joke about London, but yeah, unless you have a context of something like that, of living in a very unpredictable area. So this surprise is a very interesting quantity, and we think that the brain uses it in multiple ways, one of those being to determine the length of episodic events. And to be clear, by episodic memory here and in the title and in general, episodic memory in the context of neuroscience, we're talking about the memory system of the brain responsible for encoding, storing, and retrieving personal experiences and events. So a lot of research has shown that the points of time with high surprise are exactly the ones that we remember in our episodic memory, and that this is how we segment continuous experiences into discrete events. For instance, two events from the example before would be the period of sunny days initially and the shorter period of snow later. And how do we measure surprise? From a Bayesian perspective, we can take the negative log likelihood of the current observations the brain receives, given its prior beliefs, including very recent context, and the brain's general knowledge. And this, in LLM terms, would be equal to the negative log likelihood of the current token, given all previous tokens that the model has seen and all the model parameters. So now, a very interesting observation that was made recently is that LLMs have an inherent ability to segment episodic events similarly to humans. And that this type of Bayesian surprise correlates very well, at least in small models, with what human annotators report as events on average. And there is some nice common ground between these two mechanisms that has already been established apart from intuition. So that's great for us. So taking all this together, what we did here was to take a typical modern LLM, any LLM really, you can apply this method that I'm about to describe without using any fine-tuning, just off-the-shelf LLM, and calculate the surprise over time using the previous equation. And every time that the surprise exceeds the threshold, we identify that token as a surprising point or as an event boundary. And we use these points to split the context window into episodic events defined as an event, as in the event cognition literature I mentioned before, which can be later recalled individually. A small exception to this is a small window of the most recent tokens and the very first tokens presented to the LLM, which we always recall because for the recent ones is because they contain arguably the most important information the LLM needs. So it's like a working memory, if you will. And the first ones because previous literature has shown them to be very important in LLM performance. It's kind of a hikey thing that many approaches today use because of the way that LLMs are trained, but that's not an important point. I'm just mentioning it for completeness. Then to go even further with this, we came up with an important observation, the fact that our memory formation system should maximize the useful information within the events of the model that is going to later retrieve. To explain to you why this is important, consider the following hypothetical scenario in a very simplified example. The transformer model that you see here has received the following events that mostly contain similar types of information, colored, similar keys are represented with similar colors here in this visualization. And when a new query comes due to a new token, the model is reasonably going to recall the event with the highest similarity with this query, right? Which is this event in the middle. However, there might be a few tokens around this event that occurred after another surprising point of time, which won't be recalled because they were judged to be in a different group. And this might be because of noise, this might be because there's a second surprising thing that happened within the same sort of context. So what we need to do here is to find a way to refine these event boundaries such that similarity of the keys within a group is maximized and similarity across groups is minimized, such that we can group those four things together since they're going to be used together. And there's an easy way to do this if we treat the different tokens as nodes in a hypothetical weighted graph, as you see here. And we take the adjacency matrix of this graph and we measure some graph theoretic metrics that everything we can use to see to what extent we maximize interconnectivity while minimizing interconnectivity of a given set of node clusters, which are our events in this case. So these are the real values that you would get if you took the colors here as similarity matrices. Luckily, there are many well-known metrics to measure exactly this in clusters of weighted graphs, which we can use as an objective for an iterative refinement process, which is what we do. One example, I'm not going to give you many examples, there's no point because this is well-established literature, but one example of these metrics that we found to work well is the modularity of a graph that measures the strength of division of a network into communities. Specifically, it measures the density of links inside communities and as compared to links between communities. So this is exactly what we need, right? To assess how well this algorithm we defined works, we initially wanted to understand how good and human-like the surprise metric we capture is, because of course we have this intuition from this evidence from the literature, but we don't know to what extent this extends to larger models and the exact implementation that we have, right? So we used a series of podcasts from the literature where 200 humans were previously instructed to report the points of time where they think an event took place, and we averaged them, and we took a Gaussian filter of them to make them smoother, and we use this as indication of when humans think an event happened. This is the same data set that has been used in cognitive psychology studies that I mentioned before, as I mentioned earlier in my slides. So luckily, having access in this data meant that we didn't have to go and conduct a new experiment, but we can we can make some new meaningful insights that might help neuroscience using existing data from humans. So using this data, we took all different combinations of methods that we tested so far for segmentation. First, for initial segmentation of the model's KV cache, which is basically the things that LLMs put in memory in terms of, instead of tokens, they put the processed keys and values in memory, which is what they are going to need later for the softmax attention. And we also tried all the combinations for refinement with different graph theoretical objectives, like modularity I mentioned before, including a baseline of fixed size events, which is what InfLLM model is doing, as I mentioned initially. So we use the fixed size initial segmentation, but then we apply our refinement method even on top of that. And what we saw was that the difference between our surprise-based segmentation and what humans did is remarkably low compared to other methods in all cases, regardless of what method is used for refinement, which was really nice to see and extends much beyond what the literature has shown. Then to go one step further, we checked how the performance of this method compares in segmenting these key value pairs for each layer of the transformer individually, because different hierarchical layers usually encode different levels of representations of our data, and we wanted to see like in which layers this is more meaningful and if it makes sense in all layers to some extent. And we can see in these graphs, x-axis, the different transformer layers. In particular, here we used Llama 2 and Llama 3, so this is from 0 to 32 layers. And in the y-axis, we see the performance of its method, which is measured as the ratio of intra-group similarity versus intergroup similarity, simply. So here we saw a striking similarity between what humans do and our surprise measure, which is a very interesting result to consider if you're trying to understand how human event cognition works, really, because we took the surprise of the model in the output layer, but we're comparing the segmentation in all layers individually. And it's interesting to see that with our graph theoretically refined.
Yeah, sorry to interrupt. So the grounded truth or the human segmentation is the crosses, or which part in this graph?
Oh yeah, I should have mentioned that. I'm very sorry. Yeah, so the ground truth, exactly as you said, the human segmentation is defined by the crosses here. Actually, I don't have that in my slide, unfortunately. Apologies for that. But the blue methods represent methods that start with surprise segmentation, and with the dashed lines, we represent different refinement methods. The red curves represent fixed base segmentation with or without refinement. You see that actually yeah, sorry.
No, just to understand. So the dots are the ground truth, let's say, and the red line, the non-dotted red line, that's like InfLLM, you mean?
Exactly. The full red line is InfLLM, which we see is doing less than, is applying more like higher similarity on average to between groups than within groups, very surprisingly.
I see. Okay, got it. And the other lines, the other lines are kind of what we propose, essentially, right?
Exactly, yeah. And the full blue line again is just surprise segmentation, and the shaded area is the standard deviation of the full line to see basically how close we are to what humans do in both cases. I chose to have these two graphs in our paper. We have more graphs that show the same effect with different metrics, but I think that's in all of those, it's quite visible that what humans do is very close to what surprise segmentation does.
Got it. Yeah, exactly. So the conclusion from this graph is that we are closer to how humans perceive or segment events than, for example, inf LLM, something like that.
Exactly, exactly. And it's also interesting to see that with our graph theoretic refinement, which is not particularly, the only part here that is not particularly inspired by episodic memory, we achieve better clustering in general than both humans and surprise. So humans are arguably doing something very close to what surprise is doing. But with our model, with this simple observation that what makes a group good for recalling it later, we seem to go one step even further than that if we want to, if we apply refinement. But we'll see in the results that with or without refinement, this method of surprise exceeds performance of everything else. Yeah, and while we also saw, as you said, that the inf-LLM method performs horribly from this aspect. Yeah. So finally, we wanted to make sure that these previous points are consistent across different models and in a much larger data set than the one we used with human annotations. So we ran again the same analysis and we measured different metrics for evaluating graph clustering. And we saw that again, all variants of our surprise-based segmentation, especially when combined with our refinement method, always outperform significantly our baselines, regarding of which metric we use for refinement and which metric we use to measure it. So now that we have a great way to encode events, we still need to define the most optimized and human-like way of retrieving these events. In cognitive psychology, there are two major types of episodic recall studied. There is cued or directed recall, where specific cues are provided as stimuli to prompt memory retrieval. And there is a free recall, what we call free recall, where the participant's mind is simply left free to wander without any particular instructions or stimuli. In our case, modeling cued recall is quite simple, really, because we don't have to go very far from what alternative models have been doing in the LLM literature. As I mentioned, the transformer is already going to produce queries to look for information that might have experienced in the past, similarly to us humans retrieving old memories when we want to think something specific in particular. And so we just need to find the events that show the highest similarity with the current query and put them in a buffer that will be given to the transformer as a normal context window. So that's what we did using approximate k-nearest neighbors, which today has some very efficient implementations. So it is way more efficient than having to calculate similarity across all the events, even if you have one representative token per event. And this allowed us to store even huge lists of events in vector databases and not in machine's GPU, and allowed us to make this large context LLMs way more scalable than before. But the second case of free recall is a bit more interesting, at least from neuroscience perspective. We've seen in multiple human studies so far that the brain recalls things that happen near the time of something else that has recently recalled as well. So, for example, here this graph, if you take the point 0 of something that has been recalled, the time of an event that has been recalled before, and all these points, consecutive time points around this event, you see this effect here. And you see that the brain is giving high probability to recalling things happen after this first item, but in general gives high probability in neighboring items. So the high probability in the things that happen afterwards means that it keeps the sequence of the things happen, basically, in other words. So this effect is quite famous and known as temporal contiguity and asymmetry in free recall studies, and it was in fact very recently found in attention heads of LLMs that are mostly utilizing attention information in the context window. These heads are called induction heads in the literature, and they found to have this particular pattern, which is, as you see, remarkably similar to what the brain is doing. The trick is here to be able to give to this model the right information to be able to express this innate behavior. So this is exactly what we did. In our case, to encourage the LLM to express its behavior, we introduced a second buffer of events, what we call the contiguity buffer, that acts as a sort of a queue and maintains for some time all the neighboring events from the ones that have already been recalled due to their similarity. And having a first-in, first-out structure like a queue makes sure that we have a similar effect to the decaying constant that we see in cognitive neuroscience studies, where any contiguity effects that we see in memory wears off after a while, but it stays there for a few rounds. That's the important bit. And the only parameter we need here is the ratio between contiguity and similarity buffers in the transformer's context window. And of course, also how long the whole context window is, but this turns out to not be that important. We used 6,000 tokens for all the experiments that I'm going to present here. The most important parameter that we have is the ratio between contiguity buffer and similarity buffer. And yeah, this is basically the complete stack of transformations that define our episodic memory model, really. So to connect everything together, we ran experiments with two large benchmarks designed to assess how good a pre-trained LLM becomes in long context tasks. We compared against the model InfLLM, which, as I said, can be considered the current state of the art in long context tasks, and it's the only model we are aware of that performs some sort of KV-cast segmentation in any case. And as you can see in both tables, there's a clear supremacy of our approach. Even in the case of multi-news, there are models of our method, which, by the way, we call EMLLM, that outperform InfLLM, but we try to be consistent here, and we chose the same method of its variant to compare like apples to apples. Yeah, and we see basically a massive benefit in some tasks that require accurate use of past information, including the passage retrieval task and the hotspot QA task that that the model has to use in more than one ways previous recorded information, as well as in other long context retrieval tasks such as the math find and the KV retrieval. Just for people that don't know, both these are well-known benchmarks that papers that models that are about long context LLMs are using, but the big difference is that this is a little bit more difficult in terms of like difficulty of the actual task, whereas in infinite bench the focus is to have very, very long context windows in the scale of perhaps even millions of tokens sometimes. And you can have all that with the computational complexity that is impressively smaller than typical LLMs that we use, that they use basically the whole context window when calculating a new token. So instead of using hundreds of thousands of tokens each time, we've only used, as I said, a fixed number of 6K tokens for all our results, while the performance, when you compare it to these models in the long tasks of infinite bench, the second benchmark I mentioned goes in an entirely different league. Like basically, typical models, they're not able to solve these tasks at all. So to sum up, here we used different insights from the literature of human episodic memory to build an architecture that uses pre-trained LLMs and increases their performance substantially in long context tasks without the need of fine-tuning, and I cannot stress this enough. It does so in a much less expensive way. For example, all our experiments fit in one V100 GPU, regardless of the number of tokens in the model required to take into account, because simply the episodic memory part of our model is saved in a database outside the GPU. There is no reason to use the GPU for that. While the full LLM we would not be able to fit more than, I would say, 10,000 tokens, 12,000 tokens in the same card maximum, if in the very extreme. So due to the close relation of our approach to the cognitive neuroscience literature, it has the extra benefit that it can definitely be used for modeling human behavior. And this is, in fact, an area that we're very interested in exploring further, sort of like reducing the gap between state-of-the-art studies in AI and the human brain. And the final point I'd like to make, which is a more practical one, and again, I would like to focus, is that EMLLM provides an awesome replacement to RAG models. I don't see any benefits in using a RAG model compared to EMLLM, since it operates directly in the space of LLM queries, so it recalls by definition exactly the information the transformer would like to utilize. It works even better than full-scale vanilla transformer models, and any experiments we've conducted so far or seen so far from alternative papers will have superior performance in all cases. So next time you're planning to use RAG, please consider our method also. And with that, I'd like to thank my amazing co-authors and colleagues that made all this happen, including, of course, you, Haitham. I've been extremely lucky to be working with all you guys, and I'd like to thank you all, and the audience here for your attention.
Zaf, thank you so much. This was amazing. Thank you. Well, first of all, amazing work. I really love this work. It's super cool. It's super awesome.
Thank you.
And I'm impressed. So you want to say that we should stop using RAG and actually use episodic memory LLMs instead?
Yeah, I mean, to my mind, it's a much simpler thing to do. You just take the LLM, you take the whole architecture, you give it the things you want it to remember, and more like a human-like interaction, just to remember those things. You don't have to mess with different embeddings and all the RAG saga.
And it's really interesting that there's this connection to cognitive psychology, right? Like this is really cool. So what's the next step, you think? Like where do we go from here?
So
don't give a lot so other people take it.
yeah, actually that's exactly what I'm trying to think. How to keep a good balance between keeping it appealing but without revealing too much. So basically, episodic memory, one of the important things that is responsible to in the brain is, keeping these long-term memories, right? That, as we said, span across a lifetime. But that's not the only important thing. For example, there is a lot of work that can be done in terms of like continual learning here, and in terms of finding a balance between how many things to remember and how much memory to take for those things. So I don't want to say too much, but like improving memory complexity in LLMs as well, which is another big area that we didn't improve that much here. We've been working on it, but this paper is not about that. As well as continual learning and avoiding catastrophic forgetting are things that the brain is solving with episodic memory to the best of our knowledge. And the model that we have developed here is very compatible with how we could do as well. And yeah, so just stay in touch for our next archives.
Sounds amazing. Zaf, so thank you again for your time. This was really awesome. And yeah, as everybody, I'm looking forward to your next work. I think you want to have a short vacation, which is needed. So please go on your vacation, charge up, get some awesome ideas, and then come back to us. Thank you, Zaf.
Thank you. Thank you for having me.